Welcome everyone. This is Abhishek Majumder, and this is a joint work with Professor Philip Lindskog from Stockholm University, and the title goes by Exact Long-Time Behaviors of Some Regime Switching Stochastic Processes. So yeah, this is the structure of the presentation. So the problem is mainly motivated from the uh, time series related data, where your observed time series is explained through some function of theta and t that usually we have, and t denotes the time and theta is the unknown parameter which is fixed, usually taken to be fixed. But if we assume that instead of being fixed, if theta depends on some some stochastic underlying process, then how the stochasticity of that process will impact the long time behavior of y. So that is the main content of this work. So a here denotes the vanilla model where theta is taken to be fixed, and b denotes here that theta depends on this xt, which is the we call the regime switching process, that through xt, the theta xt, that process uh, takes different values in from the parameter space. And yeah, so that's the main question. And so the question is that how the different parameterization of xt will impact on the long time behavior, exact long time behavior of yt. So let's have an example. So as a vanilla model, or as seen, we have seen in A, this is the Ornstein-Uhlenbeck process where A and B are taken to be constant. And in that case, the state space representation looks like this. And as a simple consequence of that, if you have the drift A strictly greater than 0, then we know that yt converges to a normal distribution with these following parameters in distribution. If it's strictly less than 0, then we know that it diverges exponentially, and you have a result like this. I mean, behaves like a transient manner. And if it is equal to 0, then you see that this part is 0, so it is just a Brownian motion, multiplied with some constant. So in that case, you have a result like this. Now the question arises when instead of being constant, a and b are now functions of this underlying regime process xt, but xt is outlined as a jump type process, that is a continuous time Markov chain with a given rates lambda ij, and that is the description of this continuous time Markov chain, where this lambda ii is sum over lambda ij I not equal to j for maintaining regularity of the rate matrix. So if we assume that, so given the initial distribution of x and the lambda, the dynamics of xt is well explicit. So now further, if we assume that if x is stationary, has ergodic with having with his stationary distribution pi, then the literature, the results exist are following. So if the expected drift under pi is positive, then this yt is stable or positive recurrent, and if it is strictly less than 0, then it is transient, and if it is equal to 0 in one dimension, then it is a null recurrent. So also, I mean, in the stable case, the stationary distribution, well, it is not exactly characterized, but the tail behavior is well explicit. So if the least value that a can have uh, is positive, equal to 0, or negative, that corresponds to the stationary distribution having the Gaussian type tail, exponential type tail, or heavy tail like Pareto type. So these are the things that are in the literature, but no particular expression for this kind of value is known, and that is very much important in the rare event analysis, and also some real problems where people are interested in how this underlying stochasticity of x, the stochasticity of the dynamics of x, will impact particularly this kind of impact in this kind of value are very much important in finance and econometrics. So yeah, so that's the kind of motivation. And in order to explain the results, we had this idea of this we use this idea of the stochastic recurrence equation, which is basically a distributional recurrence of this type, which can, I mean, given a and b, x is said to have this sre if we have this distributional equation like this, and this is basically the stationary solution of a random coefficient autorecursive process like this, where AI and BI's are just IID from joint distribution of A and B. Now, for one dimension, we have that this stationary solution uniquely exists if expectation of log of mod A is less than 0 and expectation of maximum of mod B and 1, which is the log plus mod B, that is finite, and also some other condition which is only required when some non-regular cases, but for regular cases we can just omit that part. Yeah, so this is the condition, and let's look at some assumptions. We have the underlying X process to be ergodic with and irreducible on S and with a stationary distribution pi. Just to note that S is the all possible set of regimes that can be countably infinite as well. So yeah, general structure. So if since X is ergodic and irreducible on S, that implies the positive recurrence. So this is, I mean, a consequence of positive recurrence is that the length between two successive heating time to a particular state by X, that length has finite expectation. So tau for a particular set J belongs to S, denote tau not J is the first heating time to state J. Second heating time would be tau 1J, third heating time to tau 2J. There are the time instant when X hits particular state J, and then it stays there for some time, which is an exponential distribution random variable. And then it goes out, and then it comes back again to state J, and it makes recursion like this. So we all know the consequence of regenerative process suggests that in this interval, X behaves like IID for K greater than or equal to 1. So we also assume a integrability condition, which looks bad, but they are strongly implied by if we assume these two assumptions, which are not very difficult to assume, which holds mostly for all of the cases that we consider. So let's look at the result. As we told you that we do not know explicitly what is the stationary distribution before, but now the stationary distribution can be explicitly characterized, and that is a mixture of Gaussians. So as you can see, you have that marginal of x equal to as pi j, and the j is involved here as well through mu j. But what is mu j? Mu j is law of this zj and this kind of red stuff, and the red stuff involves only random quantity tj, and I'll come. Tj is a exponential distribution with tj exponential distribution lambda j, and zj is a stochastic recurrence equation as I described in the last in 2 slides before, where aj and bj are given by some particular functionals of the underlying regime switching processes in the regenerating regenerating integral. So aj and bj, given aj and bj, this dynamics zj is particularly very explicitly described, and that way you know each and every component of the stationary distribution. Now if we look at the transient case, and given the sigma j square is finite, which is like this, you have a result like this. The scale, I mean, we knew that it has an exponentially divergence, but the scaled limit has a fluctuation where it converges to mixture of some normal, where it takes basically, the mixture is basically with probability pi j, it has a variance sigma square j divided by expected interval length, which is the tau 1 minus tau naught. Now if we look at the critical case where it is expectation of a equal to 0, then obviously this term should not be there. But what happens to the right hand side? So under some integrability condition, which is very similar as previous, we have similar thing, but in right hand side we have modulus of normal instead of just normal. That is a surprising result that we have found. Okay, so this is kind of the full picture that we just described for the Ornstein-Uhlenbeck processes, and these are some illustrations of how this kind of methodologies can be extended to other directions, and some of the open questions I also listed here. Yes, so this is the bibliography, and this is the paper. This is also available in arXiv, but that is a very first draft, and In the draft, I have to mention that we also did some CIR process formulation that contains some mistake, but in the final version that we corrected it. So if you are interested, just email me. I can send you the final draft of the paper. Okay. Thank you for your attention. Thanks.